Hi, today we are revisiting the topic of piecewise functions. This is a topic that you learned about in Algebra 2 in your pre-AP Algebra 2 class, and so hopefully this is just a quick review if you need it for this topic. We learned about the piecewise definitions, which look like this last year, and we learned about graphs, so it could be a graph that looks like this or looks like this. Piecewise means it's pieces of a graph, so that's where it gets its name. The note pages from Algebra 2 in the past have looked something like this, so I went ahead and included them in the PowerPoint. You had your notes in your Carnegie book, but basically the things that we talked about in that Carnegie book is that a piecewise function is just what it says. It is a function. It's defined as a function, and the definition of a function is that it must pass the vertical line test. Piecewise functions, however, look a little different because it is a function that's made up of pieces of the different kinds of functions that we've studied. They can be continuous or discontinuous, and if they're continuous, that means we can put our pencil down on the left side of the paper, graph the entire thing all the way across the domain, and never pick the pencil up. If you have to pick the pencil up, it's discontinuous, and so you might have a jump or a gap or a hole in the graph, which would make it discontinuous. We looked at a truck driver problem, and we'll kind of talk more about that as we go. Piecewise functions consist of three parts: the name, the pieces of the function, and then where each piece of the function is defined. The pieces of the function are defined for different parts of the domain, so we have to be careful with that. So this is an example of a piecewise defined function. It has a name, and you can call it anything: f of x, a of x, b of x, whatever you like. Then it has the actual pieces, which are the pieces defined by using the different functions that we've studied. And for each of those pieces, the third thing is where it's defined. So for instance, in this one, the 2x is a linear function with a slope of 2, but the only part of that line you're going to see on the graph are the pieces of the line that fall between 0 and 2. So it takes all three things to be a piecewise defined function. So if we look at this truck driver problem, this is actually a piecewise function that consists of two lines because the driver earns two different rates. He earns one rate that's $21 per hour for the first 40 hours that he works in 1 week, but then he earns $31.50 or time and a half for work hours that he works over 40. So this is a piecewise defined function using two linear functions, and this is specifically looking at the wages as a function of the hours worked in 1 week, which we called H. So the piecewise looks something like this. We called it WH, that's its name. Remember, that's the first part of the definition. The second part is this part right here, which is the pieces. So the first week he gets 21 times the number of hours he works. The second week he gets 31.5 or 31.50 per hour he works, but then we would have to subtract off the 420, which would be the money he would have been making at 21 an hour. So if you were to add points or find or calculate points, then for instance, if I wanted to know, well, he worked 10 hours, I don't plug the 10 in the top and the bottom because that is not in my interval in both places. The number 10 actually falls between 0 and 40, so that means I take 21 times 10, and that would give me 210. It's not going to have two answers. So then if I do 30, well, 30 falls between 0 and 40, so 21 times 30 is going to give me 630. When I hit 35, still up here in this interval, so 21 times 35. When I hit 40, notice 40 is in both places, so I have to choose where it's most appropriate. So remember, he gets $21 for 40 and less, so I would have to plug the 40 in here. 40 times 21 would give me my 840. But 52.5 exceeds that 40 hour limit, so that puts me down in the bottom function, and then I would take 31.5 times 52.5 minus 420, and that's would give me the value at 52.5 hours. So you have to be careful, make sure you're not plugging in the number you're working with into the wrong piece of the function. So this was the linear function. Here are those values we just kind of calculated, and you can see the 21 hours is the line in red, and the 31.5 hours minus the 420 is the one in blue, and you can see how those two pieces come together and make that function. So if we're looking at a function here, there's a couple of ways to graph it. We talked about last year that you could just graph the whole line x plus 1 across the whole paper and then erase the part that doesn't work. So only showing the numbers 2 and less, and we would erase everything to the right of that and then connect the dots, and that gives us this piece right here. The other part is a horizontal line at 1, but we only show it for the numbers greater than 2. Greater than means not included, so you can see right here on the graph that's an open circle and it goes there. This still passes the vertical line test because when I draw the vertical line down here, even though there's two pieces that line up at the same vertical line, one is solid meaning included and one is open meaning not included, so we still have a function intact. So the other way that you could graph it is you could go to your endpoint. You can say, okay, this one's at 2. I can plug 2 in here and say 2 plus 1 is 3. I graph the point 2 and 3 with a solid circle because that is equal to, and then I can plot my my positive slope in the other direction. So I would go down 1 over, and that gets me this line. Then I can say, okay, so I'm going at 2 again, a horizontal line at 2, so I go to 2, I get the horizontal line at 1, started here with the open circle and move that way. So you can either graph from those endpoints where you have that interesting behavior, or you can graph the whole thing and just kind of erase what you don't need. So, for example, on number 2 here, this is a piecewise defined function. Its name is f of x. It's made up of 3 pieces, a line that has a slope of 3, a constant line at 6, and a line that has a negative slope and a y-intercept at 10. So the line that has a slope of 3 is defined between 0 and 2. Notice you would include the 2 here, but you wouldn't include it there. So anytime you have numbers that line up like this, remember we talked about last year the fact that if it's open circle to begin with and the second piece of it fills it in, now the whole endpoint is filled in. You can't have an open and a closed. You have to just fill it in. Okay. So if I graph this on my graph, it's going to look something like that. Remember this 2 here, even though it isn't included here, it is included there, so that becomes a solid dot right there, not an open. So be very careful. This one is open because the 0 is not included in the first function. So there are 3 here we're going to look at really quickly and just give you a little refresher. The first one is g is its name. We have a square root function that has a horizontal shift to the left 3. We have a quadratic function that's going to shift to the right 2. And we have a linear function that has a y-intercept at 4 and a negative 1 slope. And then it shows you each piece that it's defined. So when we graph these on the graph, this top one, and we can see we have a little quadratic there and we have a little linear over there. Paying attention to those endpoints is really important since none of them actually overlap at the same dot, but they do have a solid and an open on the same vertical line. So that means if I do domain from left to right across my graph, I'm going to go from negative 3 and include it all the way across to 7, and I wouldn't include it because that's an open dot right there. Range is bottom to top, so you'd start down here at negative 3, work your way up to 4. Notice that even though there's an open circle here, there's a solid one here and here, so there is a number on that horizontal plane, so you don't have to skip any of those numbers. And then finally the zeros would be where it's actually touching the x-axis, so that's going to be here, here. That's an open circle, so it's not touching, so you just have the values x equals negative 3 and x equals 2. Moving on to question 2. This is a piecewise function that has a linear function with a slope of 3 and a y-intercept of 6. We have a cubic function and we have an absolute value function that has been shifted to the right 3. So when you graph the line, you're only going to show the line at negative 1 and less. A quadratic only between negative 2 and 2. Remember to include it, the negative 1 here, but not include the 2 there. And then the absolute value is going to go from 2 to 6, including in both ends. So when we get that on the graph, it looks something like that, kind of a funny looking graph there. So keep in mind domain is left to right. I have an open and a circle, closed circle that line up here, an open and a closed circle that line up there. So I can say that my domain is going to go from negative infinity to 6, and it would include 6 because that is the endpoint. The range would be bottom to top, so we're down here in negative infinity land, so we're going to go from negative infinity all the way up to 8 because horizontally there is a dot here, so we can include that. And then finally where it crosses the x-axis, which is going to be at negative 2, at 0, and at positive 3. So we'd have those zeros. Okay, the last one, practice problem 3. We have an absolute value function that shifts to the left 2, a square root function that shifts to the left 1, a quadratic function that shifts to the right 4. So you're only going to see less than negative 1 for the absolute, between negative 1 and 3 for the square root, and between 3 and 5 for the quadratic, paying attention to those endpoints. So it's going to look something like that. So as I do my domain, I'm going left to right, and I see an open and closed circle that lined up, but look what's going on right here. I have 2 open circles. That means there is no vertical point on the 3 line to include in my domain, so I do need to skip over that piece of the graph. The range is bottom to top, so we're starting at the x-axis, so we're going to have it from 0 to all the way up there, and when I go from 0 to positive infinity, keeping in mind, even though I have open, open, open on this horizontal plane at 1, I still have that line crossing right there that's going to provide me with that horizontal value. And then we have our zeros, x equals negative 2, x equals negative 1, and x equals 4. So those are some of the things that we've talked about. If you're struggling or need a little review, there is a document on Canvas that reviews all of the parent function graphs from Algebra 2, as well as the ones we spoke and learned about earlier this year, the greatest integer function, the absolute value function that's absolute value x over x, those things that we learned this year. There is a file that goes over all of those if you need a quick refresher. The last thing last year we talked about is if we were going to do this on the calculator, which is really not such a big deal to us right now, but if we were, we can use the piecewise function and the restriction and actually put it in the calculator if you wanted to see it graph. So I just did 3 just to refresh your memory, but you would put in y1 and you would take that absolute value of x plus 2. Notice that's all in parentheses. Then you divide, and then you put in your restriction. My restriction was x less than negative 1. I have found that doing each piece separately tends to get a little bit better graph. With the new operating system, that may not necessarily be the case, and if you have forgotten where to get those inequality symbols, you go to your test menu. So you do second math and you get this test list, so you can get the less than, greater than, less than, equal to, so you can actually put it in this piece. A couple of words of caution: be sure you have a full set of parentheses around the function, hit your divide sign, and then a full set of parentheses around whatever your restrictions are. So even though there's parentheses around this piece and this piece, you still need that set around the whole thing to make it actually graph. And so I showed you 2 pictures of the graph here. We have this one, but since it was really hard to see right here what was going on, I turned off the axis so you could actually see the piece of it graphed there. So we're not going to do a whole lot of graphing with piecewise functions. We are going to be using them as we start studying limits. Limits is a very, very important topic for calculus, and it is something you really need to kind of get a good grasp on. Not so much that you will just technically isolating looking at limits, but the piecewise graph is modeled in position graphs, velocity graphs, acceleration graphs, and so having an understanding of what's going on that piecewise graph can be very important to taking care of some of those calculus problems. So the lesson that's coming up next will actually be a pretty big lesson over all of our limit techniques. We'll talk about continuity, we'll talk about limits to infinity, we'll talk about algebra techniques for evaluating limits. It's a really, really, really important topic for calculus. It's not a hard topic, but it is very critical that you make sure that you're processing and getting that information. So I will see you next time for our lesson on limits.